Hi, welcome back to the online static review sessions. In this session, we'll talk about internal forces, which are important for the following session, especially that when you start learning about the shear moment diagram. Internal forces are forces that when you cut through the member, you will see shear, normal, and moment forces. When you don't cut, these are the forces that resist actually the failure of the member. Will help in the future in calculating or finding the stresses based on the cross section and further design of the member. But the first step is finding these internal reaction or internal forces. These internal reactions again are composed of the shear force that is parallel to the cross section or perpendicular to the center line of the member, a normal force which is normal to the cross section or perpendicular to it, and a moment that rotates at this, whether it is clockwise or counterclockwise, it depends on how the calculation would show you. When you cut through the member, you will see the same forces, internal forces on both sides. They are equal but in the opposite directions. Please don't get confused the difference and be careful the difference between cutting through the member and taking it apart at a pin. A pin has no moments, so it has only the pin reaction. Some would draw by mistake a moment when they take it apart at a pin. And this is totally different because we're talking about pin reactions. Here we talk about internal reactions or internal forces, shear, normal, and moment. We will, for now, stick to this assumption. Whenever you cut, you look to the left, and I will talk this especially in next session when we work with the shear moment diagrams, because it will help us also in knowing what is the direction. So whenever you cut and look to the left, give the assumption shear is going down, normal coming out, and moment counterclockwise. And if you look to the right, normal to the left, shear up, and moment clockwise. This is important, you'll see when we come to shear and moment diagrams. So let's do an example on this beam. You have a beam that is supported by a pin support and a roller support, and here we need to find the internal reaction to the left and to the right of this concentrated load at point C, and also find the internal reactions at point D. So we start by looking at, it's similar to the method of section of trusses. Whenever you find forces, you look which side you would work with, because internal means that you have to cut and then use either side to work with. For the sake of exercise, I will use the right hand side. Um, Although this is much easier, but I work with the right hand side for more exercise. You notice at the right hand side has this support reactions at BBY. It is roller support, which means that I have first to find it from the whole system before taking the cut. So the best way to find that is moment about point A, uh, and then you write the moment equation. So you have B y times the moment arm. Counterclockwise is positive, and then you take this force, the vertical component of that force, which is the opposite to the angle 60, which means that we have to use the sine the angle, and then multiply it by the moment arm is 3. Um, Rotating clockwise negative. Notice that the horizontal is not, it's just passing through the point of rotation, so we don't need to worry about. The followed by the 15 multiplied by the moment arm perpendicular distance to the point, and 7, and then finally this distributed load. The distributed load is we first find the resultant, which is 5. It's nothing more but the area of this rectangular shape. So it's the 5 the height times 6 the base, and times moment arm. So the concentrated load or the resultant of this distributed load acting exactly at the centroid of the rectangle, which is a halfway at 3, and then add to that. Now we're taking a moment about this point, so you have to add to that 5, 4, and 3, and this will give you the reaction at point BBY equal 4755 pounds. The following step is to take the cut. So we would like to find the internal reaction to the right and left of that concentrated load at point C. So we draw both sections. So I cut here once with that force at point, and because I'm cutting right to the left of it, and the other one is without the force because I'm cutting to the right of it. Notice in both cases I'm using the right hand side because I just found also the support reaction. So I draw the internal forces in both cases. So you have the internal reaction shear, normal and moment in both, and then I start applying equation of equilibrium on each. So we'll start with the one without that force or to the right of it. Some of the forces in the X, because you don't have any force else that is parallel to the member, or which means that NC or the normal at C would be 0. Forces in the Y, you have that shear force, you have the By that we just found, and then you have the distributed load, and we use the resultant of that is 5 times the distance here is 6, height times base, and then it gets you a negative 17.55 kip, which means it has to be directed downwards. Um, Finding the moment, followed by to find that internal moment MC. So you start By times the moment arm 5, and then MC is rotating clockwise negative, and then also we need to find that moment caused by the distributed load. So you have 5 times 6 the base times the distance 8, which is this acting exactly as half the distance, and then add to that 3, add to that 5 is 8. This will give us also as a negative 225 pound-foot, which means it has to be rotating clockwise or the opposite to the assumption. For this case, there will be no change in the x direction. It's exactly as this one, but there will be change in the y direction for the shear. So the shear here, the only difference between these two equations is in the inclusion of that concentrated load 15 with its sign negative. So you have also the shear, the By, and the resultant, and then finally the shear force would be 255. It's negative, so it has to be directed downward. Notice here the difference between to the right and to the left is simply the 15 kip. And then after that, you will find the moment. So the moment in that case is no difference if you look, because this 15 is exactly acting in a point, and you're taking also the moment at point C, so there's no change in the moment. A good observation and comment that you can see when you cut here from, we're always moving from the left, so you cut from the left and you see that 255, and then it will increase in negative because there's a drop. This is important when you look when we work with shear moment diagrams. There's a drop. The difference increases from -2 to -17.55. This is the only difference is that concentrated load. Following is that we need to find the internal at point D. So at point D, we take the cut And obviously, it's much easier to look on the right hand side. So this is all what we take. Please be careful whenever you take the cut at a distributed load. You have to take the portion related to that part that you took the cut with. So drawing the internal reaction, and also I would draw here the uh, resultant of the distributed load and its location halfway to the 2.5. Followed by that, applying equation of equilibrium. Normal is 0. Obviously, there's no external normal. And then shear, you have the shear force, and you have another vertical, which is the 5 kip multiplied by the distance you take the cut to. So it's 2.5 and it's 12.5. It's positive, so right assumption. And then finally the moment, which is you take the moment rotating here clockwise negative, and then also this rotate clockwise, so it's 5 times 2.5, the distance, to get the resultant, and then times the moment arm, which is halfway, 2.5 half, or 1 to 1.25. This will give us a moment of negative 1563, which means it has to be in the opposite direction of that, or in a counterclockwise. Um, Final notes, please pay very good attention whenever you take the cut to pay attention to the direction, the moment arms also, where are you taking the moment from. And next session we'll start talking about the shear and moment diagram, and before going in that, I want you to review carefully this current session, the internal forces, because we will be working with that in the next session a lot. Thank you, and see you in the next session.